In this module, we start with some examples of delta theorems, what we have discussed in our last module. That is, we start with finding large sample distribution of sample coefficient of variation and sample generalized variance. Then we pass on to another important aspect of delta theorems, namely delta theorems for vector valued functions. Actually, in our last modules, we have discussed delta theorems using univariate random variables or multivariate random variables. But in this case, we shall discuss delta theorems where the function itself is vector valued. Then we shall apply this delta theorem to find the large sample distribution of sample moments and hence to find the large sample distribution of sample skewness measures. In fact, we shall discuss finding the large sample joint distribution of different sample moments of different orders, but we emphasize on finding the large sample distribution of the sample skewness measure. So, in this module, we start with finding the large sample distribution of sample coefficient of variation. This is an application of the delta theorem what we have discussed in our last module. Suppose xi are IID with mean mu and variance sigma square, and we assume that the fourth order moments are finite. Then the population coefficient of variation is defined as capital V equal to 100 times sigma divided by mu. Naturally, a consistent estimator of the above is small v, which is 100 times small s divided by x bar, assuming x bar not equal to 0, where s is the sample standard deviation and x bar is the sample mean. Suppose the asymptotic distribution of small v is required. First of all, since we have already found the joint distribution of 1 by n summation xi minus mu whole square minus x bar minus mu whole square, we first try to represent v in terms of these. So, we are fortunate enough to find such a representation. That is, we can write our small v as 100 times square root of 1 by n summation xi minus mu square minus x bar minus mu square whole thing divided by x bar. So, using our previous multivariate CLT, we have square root of n multiplied by square root of n multiplied by a vector with components t1n minus theta 1 and t2n minus theta 2 is asymptotically bivariate normal with dispersion matrix sigma, where theta 1 equal to 0 and theta 2 equal to sigma square, and sigma is, as defined earlier, is a 2 cross 2 matrix with first row having elements mu 2 and mu 3 and the second row having elements mu 3 and mu 4 minus mu 2 square. So, as earlier, T1n is 1 by n summation xi minus mu and T2n is 1 by n summation I from 1 to n xi minus mu square. So, we have discussed the joint distribution, the asymptotic joint distribution of T1n and T2n. So, we can apply delta theorem by using some suitable function g. So, in this case, we find that gxy should be defined as 100 times square root of y minus x square divided by x plus mu. Then gxy is a continuous function and has continuous partial derivatives in the neighborhood of theta 1 theta 2. Now, a little bit algebra gives the gradient vector of g evaluated at theta 1 theta 2 as a vector as a two component vector with first component as minus sigma divided by mu square and the second component as 1 by 2 sigma mu. And we find that since we have assumed mu not equal to 0, we find that this gradient vector is different from the null vector. Hence, we can apply delta theorem and using delta theorem with multiple variables, we find that square root of n multiplied by small v minus capital V converges in distribution to a normal variable with mean 0 and variance as given in the slide in the form of a quadratic form, and a little bit algebra finally expresses the asymptotic variance as capital V square whole thing multiplied by mu 2 by mu square plus mu 4 minus mu 2 square by 4 sigma to the power 4 minus mu 3 by mu sigma square. Often we have the underlying distribution as normal, and in such a case, since normal distribution is symmetric, we have mu3 equal to 0, and using some results on moments of even order, we find that mu4 equal to 3 sigma to the power 4, and hence in such a case asymptotic variance reduces to v square by 2 multiplied by 1 plus 2v square divided by 10 to the power 4. Next we pass on to some other aspect of some other application of delta theorem, namely in finding the large sample distribution of generalized variance. So suppose x alpha are IID p-variate normal distributions, p-variate normal observations with mean mu and dispersion matrix sigma, and we assume that this dispersion matrix sigma is positive definite. Now define the SSSP matrix as A, which is defined as summation alpha from 1 to n x alpha minus x bar multiplied by the transpose of x alpha minus x bar. The sample generalized variance covariance matrix is defined as the determinant of S, which is defined as A divided by small n. Now it is well known that A is positive definite with probability 1 if and only if n greater than or equal to p, and A has a Wishart distribution with p-variate Wishart distribution with parameters n and sigma, where small n is defined as capital N minus 1, and we have taken capital N samples. Suppose we are interested in the asymptotic behavior of the sample generalized variance. So first of all, we need to use Bartlett decomposition. That is, we can write determinant of A divided by determinant of sigma as product of Vi for I equal to 1 to p. That is, the distribution of determinant of A divided by determinant of sigma is equivalent to product over I from 1 to p Vi, where Vi has a chi-square distribution with n minus I plus 1 degrees of freedom, and these Vi's are independent for each I. Now determinant of A is simply determinant of A divided by n to the power p, and hence determinant of S divided by determinant of sigma has the same distribution as the product I from 1 to p Wi, where n Wi has a chi-square distribution with n minus I plus 1 degrees of freedom, and this Wi are also independent because of the independence of original variable Vi. Now expected value of Wi is nothing but n minus I plus 1 divided by n, because the chi-square variable has the expectation as its degrees of freedom, and we also get the variance of Wi as 2 times n minus I plus 1 divided by n square, and this also follows from the fact that a chi-square variable has a variance 2 times its degrees of freedom, and hence we get from multivariate CLT that the vector with elements W1 minus 1 divided by square root of 2, W2 minus 1 by n divided by 2 times 1 minus 1 by root n, 2 times 1 minus 1 by n, and up to Wp minus 1 minus p minus 1 upon n whole thing divided by 2 times 1 minus p minus 1 upon n, has a p-variate normal distribution with mean vector 0 and dispersion matrix IP, which implies that square root of n W1 minus which implies that the vector with elements square root of n W1 minus 1, square root of n multiplied by W2 minus 1 up to square root of n Wp minus 1 has a p-variate normal distribution with mean vector 0 and dispersion matrix 2 times IP, that is 2 times the identity matrix of order p. Now we take our g function as g, which is a function of the variables u1 u2 up to up, which is defined as summation a product of I from 1 to p uy, which is continuous and has continuous partial derivatives in the neighborhood of theta 1 theta 2 up to theta p, and in this case it is very easy to find that this theta equal to 1 for every I. Thus the gradient vector at theta 1 theta 2 theta p for g is nothing but a vector with all components unity, and hence we find that square root of n multiplied by determinant of S divided by determinant of sigma minus 1 converges in distribution to a normal distribution with mean 0 and variance 2p. Now we pass on to our next topic, which is related to delta theorem for vector valued functions. So we pass on to our next topic, which is on delta theorem for vector valued functions. Let GU be a vector valued function with Q components such that GU is nothing but a vector with component functions as G1, G2 up to GQ. We define the matrix capital G, which is of order Q cross P, as with elements the partial derivative of Gi. That is, the elements of G are simply delta the partial derivative of Gi with respect to Uj for different values of I and j. And we assume that G is continuous in a neighborhood of theta. If for a sequence of vector valued random variables xn, square root of n xn minus theta converges in distribution to x, then square root of n gxn minus g theta converges in distribution to a random variable which is g times capital X. In particular, if x has a p-variate normal distribution with mean 0 and dispersion matrix sigma, then the limiting distribution of gxn comes out as q-variate normal with mean 0 and dispersion matrix g sigma g dash, or the transpose of G. However, the proof requires some further concepts of mathematical analysis, and we skip the details. Anyone can find this proof in the book by Surfling, and we are not going to details of this proof. So let us concentrate on applications of this theorem. As our first example, consider the joint distribution of sample mean and variance. Suppose xn are IID with finite mean mu and variance sigma square, and fourth order moment mu 4. Define rth order raw moment m dash r as 1 by n summation I from 1 to n xi to the power r, rth order central moment as 1 by n summation I from 1 to n xi minus m1 dash whole to the power r, and the rth order pseudo moment mr naught, which is defined as 1 by n summation I from 1 to n xi minus mu whole to the power r. Then for any r not equal to s, it is easy to observe from multivariate CLT that the limiting distribution of mr naught and ms naught is bivariate normal with mean vector 0 and dispersion matrix sigma, where dispersion matrix sigma has diagonal elements mu 2r minus mu r square and mu 2s minus mu s square, and the off diagonal element as mu r plus s minus mu r multiplied by mu s. And this can be obtained just considering the fact that xi's are IID, means xi minus mu to the power r are also IID, and the covariance between xi minus mu to the power r and xi minus mu whole to the power s mu r plus s. The off diagonal element structure of sigma can be justified from the definition of mr naught, because variance of mr naught is nothing but 1 by n multiplied by variance of x1 minus mu whole to the power r, which after a simple setup obtained as mu 2r minus mu r square, and the covariance between xi minus mu to the power r and xi minus mu to the power s is nothing but mu r plus s minus mu r multiplied by mu s. Now we have the representation that m1 dash equal to m1 naught plus mu and m2 equal to m2 naught minus m1 naught whole square. Then square root of n m1 naught minus 0, that is the large sample distribution of m1 naught and m2 naught is again bivariate normal with mean 0 and dispersion matrix sigma, where the dispersion matrix sigma has the elements mu 2 and mu 3 in the first row and mu 3 and mu 4 minus mu 2 square in the second row. Now looking at the above representation, we define the vector valued function g with elements u1 plus mu and u2 minus u1 square. Then we get the 2 cross 2 matrix G as I2. Hence, using the above result, that is above delta theorem, we get that the large sample distribution of m1 dash and s square is again bivariate normal with mean vector 0, and dispersion matrix in this case is sigma, because G is obtained as the identity matrix of order 2. Next, we consider joint distribution of sample moments. Suppose xn are IID with finite mean mu and variance sigma square, and we assume that moments up to order 2r are finite. So in this case, it is already discussed that the joint distribution of pseudo moments are easy to obtain and it follows from multivariate CLT. So, in order to find the distribution of MR, that is rth order central moment, we first express MR in terms of the pseudo moments, and this is not a very difficult task because 1 by n summation xi minus m1 dash whole to the power r can be looked upon as 1 by n summation I from 1 to n xi minus mu minus m1 naught whole to the power r, and expanding this quantity in a binomial theorem, we ultimately find the relationship, that is MR equal to MR naught minus R choose 1 multiplied by MR minus 1 naught M1 naught plus up to minus 1 to the power R M1 naught whole to the power R. Thus, it is easy to take the G function. Obviously, in this case, if we are interested in finding the distribution of MR, then G is just a real valued function, but with multiple arguments. So, in this case, we define the G function as given above, and hence one can find the large sample distribution. So, we start from multivariate CLT and find the large sample distribution of M1 naught, M2 naught up to MR naught as R variate normal with mean vector 0 and dispersion matrix sigma, where sigma has the elements mu I plus j minus mu I multiplied by mu j. Thus, in this case, theta equal to, that is theta vector equal to 0 has the elements 0, mu 2, mu 3 up to mu r, and G satisfies all the conditions regarding continuity and differentiability with the gradient vector as a vector with elements with first element as minus r times mu r minus 1, and then the last element as unity and the rest elements are all 0, and naturally this gradient vector is non-zero. Thus, by the delta theorem, square root of n mr minus mu r converges in distribution to an univariate normal distribution with mean 0 and variance as given in the text. Now, after a routine manipulation, one can find this large sample variance as mu 2r minus mu r square minus 2 times r multiplied by mu r minus 1 multiplied by mu r plus 1 plus r square multiplied by mu 2 multiplied by mu r minus 1 square. Actually, it follows from the development that square root of n mr minus mu r and square root of n mr naught minus mu r minus r mu r minus 1 multiplied by square root of n m1 naught minus mu 1 have the same asymptotic distribution, and this is true for every r. So, one can find in general different moments distributions. So, for the joint asymptotic distribution of MR and MS, we note that this joint distribution of MR and MS is nothing but the joint distribution. However, for the joint asymptotic distribution of MR and MS, we consider the representation what we have discussed in our last presentation page, and then we can write this root over n. We can observe that the asymptotic joint distribution of MR and MS is same as given in the text. Now, the asymptotic distribution of M1 naught, MR naught and MS naught is nothing but 3 variate normal with means vector 0 and dispersion matrix sigma psi, where psi is given in the text, and therefore, the large sample distribution of MR and MS is just a routine and we skip the details. However, after a straightforward manipulation, one can find that the large sample dispersion matrix of MR and MS has elements sigma rs, which is defined as mu r plus s minus mu r times mu r multiplied by mu s minus r multiplied by mu r minus 1 multiplied by mu s plus 1 minus s multiplied by mu s minus 1 multiplied by mu r plus 1 plus r multiplied by s multiplied by mu r minus 1 multiplied by mu s minus 1 whole thing multiplied by mu 2. Now, next we shall discuss our next example, which is on joint distribution of multiple sample moments. As earlier, we assume that xn are IID with finite central moments up to order 2k. We can recall the definitions of central moment and pseudo moments, and since m1 equal to 0, we define m vector as a vector with elements m2, m3 up to mk, and we require to find the joint asymptotic distribution of this m vector. In particular, using the delta theorems, one can easily arrive at the fact that the asymptotic joint distribution of m2, m3 up to mk is a k-variate normal distribution with mean vector 0 and dispersion matrix sigma, where sigma is a dispersion matrix with order k minus 1 and with elements sigma rs, and this sigma rs can be found in the presentation. Now, let us discuss some interesting facts about this asymptotic joint distribution. Assume that the underlying distribution is symmetric about origin and has finite even order moments of all orders. Then it is easy to observe that mu r equal to 0 for order, and mu r is a finite positive quantity if r is even. Thus, for such a distribution, we find that sigma rs equal to 0 whenever r plus s is odd. Then, from the properties of multivariate normal distribution, it follows that mr and ms are asymptotically independent whenever r plus s is odd. For example, one can check that for such an underlying distribution, m2 and m3 are asymptotically independent with marginals univariate normal. Our next example is related to finding the large sample distribution of sample skewness coefficient. Suppose xn are IID random variables with finite 6th order moment mu 6, and then the population skewness coefficient is defined as gamma 1 equal to mu 3 by mu 2 to the power 3 by 2, provided mu 2 is positive, and since mr is a consistent estimator of mu r for any r, a consistent estimate of gamma 1 is g1, which is defined as m3 divided by m2 to the power 3 by 2, of course if m2 is positive. Thus, we find that g1 is a function of two central moments. Now, in order to obtain its asymptotic distribution, we define guv, that is g function, as v divided by u to the power 3 by 2, which is continuous and has continuous derivatives except for u equal to 0. Now, from the previous example, we find that the large sample distribution of m2 and m3 is bivariate normal with mean vector 0 and dispersion matrix sigma, where this sigma matrix has elements sigma 2 2, sigma 2 3 and sigma 3 3. Now, a straightforward calculation gives the gradient vector of g evaluated at mu 2 mu 3 as minus 3 times mu 3 divided by 2 times mu 2 to the power 5 by 2 and mu 2 to the power minus 3 by 2, and hence we obtain the large sample distribution of g1 as normal with mean 0 and variance tau 1 square, where tau 1 square is a function which can be expressed as gamma 1 square multiplied by some function of mu 2, mu 3, mu 4, mu 5, mu 6. We refer the interested reader to the book by Surfling for an explicit expression of h. However, if the underlying distribution is standard normal, since g1 is invariant to location and scale, one can without loss of generality consider this standard normal assumption. Then mu 3 equal to 0, mu 5 equal to 0, that is all odd order central moments are 0, and mu 4 equal to 3 and mu 6 equal to 15, and hence we obtain the large sample distribution of g1 for normal parent as univariate normal with mean 0 and variance 6. Next, we shall discuss convergence rate for the sample skewness coefficient. We have seen asymptotic normality of sample skewness coefficient. Naturally, the choice of n ensuring asymptotic normality depends on the underlying distribution. So, it will be interesting to study the convergence rate for different parent distributions. For our purpose, we consider a gamma distribution, a log normal distribution and beta distribution, and a standard normal distribution with parameters specified as in the slide. For each of these distributions, we simulate the histogram of the variable square root of n multiplied by g1 minus gamma 1, considering n equal to 40, 80 and 120. Now, it should be noted that gamma 1 equal to square root of 2, 6.18 and minus 0.596 and 0 respectively for the above three candidate distributions. The histograms can be found in the next few slides. So, what we observe? Looking at the histograms, we find an interesting fact. For normal parent, convergence to normal is achieved for n equal to 80. However, for gamma distribution, we get a positively skewed distribution for n equal to 40 and 80, and then normality is reached for n equal to 120. For log normal distribution, we find a positively skewed distribution for all chosen values of n. However, for the beta distribution, we get the histogram of a negatively skewed distribution for n equal to 40 and 80, and then symmetry is reached for higher choices of n. Naturally, convergence rate to normality is the lowest for log normal distribution. Now we know that both gamma and log normal are positively skewed, and beta with specified parameters is negatively skewed. So at this point, it is interesting to note that for positively skewed parents, we get a positively skewed distribution, and for negatively skewed parent, we get a negatively skewed distribution of sample skewness coefficient in small samples. However, in short, non-normal parent makes the rate of convergence slower. So we have just seen how to derive the distribution, that is large sample distribution of sample coefficient of variation, and then we have seen how to tackle vector valued functions to obtain the large sample distribution, and we have also seen the large sample distribution of sample central moments and different functions of it. Finally, we have seen the large sample distribution of sample skewness coefficient. We have seen some interesting features regarding the underlying parent and the nature of the distribution in small samples, and in our next module we shall discuss large sample distribution of sample kurtosis coefficient and discuss also the independence of sample skewness coefficient and sample kurtosis coefficient for normal parents, and also give some applications of this.